Okay, here's a problem. So we'll take this as a quiz problem and see how people do. If you're watching the video, you should now take this as a quiz problem. If you don't know what to do, well, you can come back in a minute. Okay, so if you've done this, great. If not, let's see what you need to know in order to solve this problem. First of all, we know that this is an exponential model because we assume exponential growth. So population function is a transformation of the toolkit exponential function. Therefore, following could be a times 2 to the kt, assuming that the 2 to the x function is your toolkit exponential function. And that is the function that I usually use. I believe Open Math uses it as well. Another possibility is ae to the kt, which is a transformation of the exponential function e to the x. Now, in both cases, the transformation consists of a vertical stretch and a horizontal compression by factor k. Vertical stretch by factor a, horizontal compression by factor k, with the caveat that if a is less than 1, that vertical stretch is actually compression. If k is less than 1, that horizontal compression is really a horizontal stretch, okay? Also, the k here and the k here are different numbers because the k that you use for e and the k that you use for 2, the k that you use for base e and the k that you use for base 2 are going to obviously be different. If you use the same k both places, you'd have 2 different models. And then the other possibility is just b, well, a times b to the t. Now, b to the t is not really a toolkit exponential function, but you should understand b to the t. So we're going to solve this in a couple of ways, okay? So let's start with the a, b to the t form. And let's construct a graph. Now, we don't know for sure what kind of numbers we're going to put on this, but we need room for 70 and 190 and room for 2 and 8. 2 and 8 would be on the time axis. 70 and 190 would be on the population axis. We can't just put 2 random points down because they have to be in proportion. So let's just say we want to put 2 months here. Sorry, 8 months here. And 2 months halfway back to the vertical, the y-axis, and then halfway from there, puts 2 about here. Then we have populations 70 and 190. Okay, well, I'm going to leave myself some room. So I'm going to put 70 about here. And 190 is almost 3 times 70. So I'm going to say maybe 190 is here. This is not totally accurate, but it's not too far off. Okay, so we need an exponential function that passes through these 2 points. Coordinates of those points are 270 and 8, 190. There are ways we can make this graph accurate by estimating what the half-life would be and projecting that backwards. But we're not going to do that at this point, especially since this is a support course. But we want to get 2 equations and 2 unknowns, just like we do if we have 2 points on a graph of a linear function. I'm going to choose the a, b, and the t. Okay, so if p equals a times b to the t, what's the value of a? What's the value of b? Stop and see if you can get 2 simultaneous equations in 2 unknowns. These equations will be pretty easy to solve. So see if you can write down the 2 equations and 2 unknowns that correspond to this situation. We've got 2 points on the graph. Okay, hopefully you paused and done that. Okay, the first point has t coordinate 2 and p coordinate 70. So first point. Well, if we put those numbers into the equation, we get 70 equals a times b to the 2nd power. Second point. T equals 8, p equals 190. So we get the equation p, which is 190, equals a times b to the t, and t is 8. So now we have these 2 simultaneous equations that we need to solve to find the values of a and b. Once we know the values of a and b, then we have a perfectly good formula that we can use to answer questions about this model. Okay, well, it's fortunately pretty easy to do this. Okay, if my equation 1 is ab squared equals 70, and equation 2 is a b to the 8th equals 190, then what can we do to solve for a or b? There are a number of things we can do. We could solve the first equation for a. We would get 70 over b squared. We'd replace this a by 70 over b squared, and we get b to the 6th equals 70 over 190. Sorry, b to the 6th equals 190. Okay? And I'm not sure I said all that right. Well, we're going to get something equivalent. What I'm going to do is I'm going to do equation 1. Matter of fact, I'll do equation 2, sorry, divided by equation 1, which means I divide the right-hand side of equation 2 by the right-hand side of equation 1, the left-hand side of equation 2 by the left-hand side of equation 1. And I get ab squared over ab to the 8th equals 190 over 70. Then I use my rules or exponents and so forth. The a divides out, and I end up with b squared over b to the 8th. Well, I could do that immediately, but I want to be sure we understand every step. So I got b squared over b to the 8th, and 190 over 70. Still write this as a fraction. I don't want to convert this to a decimal at this point. It's always best to keep the fractions and then until we're sure we're not going to get something that's easier with fractions than with decimals. This is going to turn out to be easier with decimals. Okay, b squared over b to the 8th. What's b squared over b to the 8th? Well, that would be, uh-oh. Okay, what did I do here? I did something wrong here. In this step, you're supposed to divide the right-hand side of equation 2 by the right-hand side of equation 1. Well, 190 is the right-hand side of equation 2. 70 is the right-hand side of equation 1. Okay, on the left-hand side, the left-hand side of equation 2 should be divided by the left-hand side of equation 1. And I wrote the left-hand side of equation 1 divided by the left-hand side of equation 2. So what I should have written was AB to the 8th divided by AB squared. And of course, that gives us B to the 8th over B squared. And you probably see what we're going to get next. Let's be sure B to the 8th over B squared. Now, when we divide B to the 8th by B squared, we get B to the 6th, and that's equal to 19/7. And how do we solve for B? Well, there are two. Well, we take the 6th root of both sides, but 1/6 power, because all this uses is the rules of exponents, which everybody should know well by this point. I'm going to raise b to the 6 to the 1/6, which is going to give me b to the 6 times 1/6, which is just b to the 1. It's my rationale for taking the 1/6 power. And it's easy to do the 1/6 power in your calculator, which you're going to have to do. Okay, well, if I take the 1/6 power of the left side, I have to take the 1/6 power of the right side. So I get b to the 6th raised to the 1/6 equals 19/7 raised to the 1/6. Now, b to the 6th to the 1/6 is, I'm going to write it out in gory detail, b to the 6th times 1/6 equals 19/7 to the 1/6. 6 times 1/6 is 1. So b to the 1 equals 19/7 to the 1/6. Now, 19/7 is a little less than 3. Square root of 3 is 1.732. So square root of 19 probably is about 1.6 maybe. And then the 1/6 power of that would be maybe 1.17. So I'm just going to say that b is approximately 1.17. Square that, we have 1.36, square that, as long as we get something close to 1.7, and square that, we get something a little less than 3. Okay, now I'm not totally confident of that. Use your use your calculator to get the accurate amount, but I'm going to use this approximation. B is approximately 1.17. So now we know that our model is P equals A times 1.17 to the T. Now we still don't know what the value of A is. So we're going to have to work out the value of A, but since we've already got the value of B, we can plug that value into our form, into either of our equations, and solve for A. So I'm going to use the first equation. We substitute B equals 1.17 into equation 2. Now let's do equation 1, sorry. To get 1.17 times B squared, never mind. To get A times 1.17 squared, we substitute B equals 1.17. Here's B. It's going to be A times the square of B equals 70. So we get A times 1.17 squared equals 70, which is about A times maybe 1.36 equals 70. So that A equals 70 over 1.36, which is a little more, dividing by a little more than 4/3 is going to be a little more than 3/4 of 70. So I'm going to say that's approximately 54. 3/4 of 72 is 54. It should be a little less than 3/4 of 72. And that's why I'm doing my mental approximation. You don't have to know that. Okay, so we get A equals 54. So now our model is P, and I'm going to write it as P of T because P is a function of T, equals 54 times 1.17 raised to the T. Okay. Now, if we want to check this, we could plug in T equals 8 and see if we don't get P equals 190. I'm just going to say, okay, if we do the second power of 1.17, I think we get about 1.36. And if we square 1.36, we get about 1.8. And if we multiply 1.8, well, if we square 1.8, we get 3.64, so call it about 3.6. 3.6 times 54. So let's see, checking. If T equals 8, E should be 190. Well, so we write the equation P of 8 equals 54 times 1.17 to the 8, which I say is about 54 times 3.6. 3 times 54 is 162, and 0.6 times 54 is about 32. 162 and 32 gives us 194. Okay. Now, I used to be really good at mental arithmetic. I'm still pretty good at it, so I lucked out this time, and my mental arithmetic got this. Much easier, of course. We just plug this into a calculator, and I don't expect you to be able to do mental arithmetic at this level. But there it is. It's pretty close. 1.17 might well be accurate, but I'll bet it's between 1.16 and 1.18. Wouldn't bet a lot. 1.15 and 1.19, yeah, but not, wouldn't bet the farm on it though. Okay. This is poorly. If T equals 8, P should be 190. We plug in 8. And if my mental calculation is right, we're pretty close. But the mental calculation would be off by a good bit. All right, so our model is this, and we found the function model. Okay, well, we can also find the function model using AE to the KT or A times 2 to the KT. I'm not going to do both, but I'll choose to do the AE to the KT. And the reason, powers of 2 are easy to understand. At least for whole numbers, you can easily calculate 2 to any power. Well, power's big enough, you're probably going to use a calculator for it. Calculating 2 to any power between -6 and 6 should be pretty easy. Okay. Calculating E to a power, well, E in the first place is not a whole number. It's not even a rational number. If you approximate it as 2.71828, it'd be pretty accurate, but it won't be completely accurate. So why would we use E? Well, this is a this is a support course for a pre-calculus class. But the concept is simply that it's really easy to do calculus with the function e to the kt. Okay, it's e is the e to the x and e to the any kx, the easiest function there is to do calculus with. Okay, and it has some pretty unique properties that make it really a pretty neat function. So it's a very handy function in many ways. I'm not going to detail those ways. It's got a Taylor expansion that's pretty easy to deal with. A lot of other things. Okay. So let's go ahead and find the model as a form AE to the KT. If I can go here, if I go to this form without any great data. Okay, so using model AE to the KT, we get the equations. Well, what are our equations? Our points are 270. When t is 2, p should be 70. So we have the equation 70, which is the value of p equals AE to the k times the value of t, which is 2. And then we have the value 190, the p value 190, when t is 8. Okay. To solve this system, we're going to use a method similar to what we did. I'll call this equation 1. I'll call this equation 2. And say I'm going to divide equation 2 by equation 1. And I'm going to get A, E. And instead of writing k times 8, I'm going to write 8k. So the right-hand side here is AE to the 8k. That'll be divided by AE to 2k. That's going to equal 190 over 70. If I do the division here, the a's divide out, I end up with e to the 8k over e to the 2k equals 190 over 70. Using the rules for exponents, when I divide same base to one power by that base to a different power, I'm going to subtract the bases. I'm having trouble writing 8s today. I don't know what this is, but e to the 8k minus 2k. Writing this out carefully. And I'll reduce 190 over 70 to 19/7. I could have done that back here. I was concentrating on this. And we get e to the 6k equals 19/7. Okay. How are we going to solve this for k? It was easy to solve for k in the previous problem. It was easy to solve for b in the previous problem. But solving for k, we have k is in the exponent of an exponential function. So what do? Well, we use the conversion to logarithmic form. And we might write down one form or another of the equivalent equations. B to the A equals C is equivalent to log base B of C equals A. And now we can identify A and B and C, well, A, B, and C. Okay. We have e to the 6k, so B would be E, A would be 6k, and C would be 19/7. So I'll just say down here using B equal to E, A equal to 6k, C equal to 19/7. I don't have room to write it down here, so I'll just come up now. And this gives us the equation log base B of C equals A. B is E, so we have log base E of C. C is 6k. Uh-oh. No, I wrote it down wrong. A is 6k. C is 19/7. Why did I say C is? Okay, anyhow, 19/7 equals C. Sorry, equals A. We're looking at this form. B equals E, so E's going to go here. A is 6k, so A is going to go over here. C is 19/7, so C goes here. So we get 6k over here. Now that's really easy to solve for k. Keep in mind that log base E of 19/7 is something you can simply punch into your calculator. You don't have a means for calculating that. Take a year of calculus, you'll learn about Taylor series, and you can see you could calculate it using Taylor series. That'd be a bit of a pain though. You don't want to have to do that. So pretty much use the calculator. Well, log base E is a natural log. And since you have a natural log button on your calculator, we're going to write this as natural log of 19/7. And then we write out the natural log of 19/7. Now, I don't know what the natural log of 19/7 is, but 19/7 is pretty close to E. Okay. It's pretty close to 2.7. I didn't make it up that way. So I'm going to say it's a little shy of, it's 2.7. Oh man, it's 2.714 as opposed to 2.71828. So I'm going to just say this is maybe 1.01. So that K is approximately equal to 1.01 over 6, which is approximately 0.17. Okay, I want to try to estimate more decimal places than that, although I think I kind of could. It's about 1.67. Okay, in any case, got our value of K, and we can plug that value into either of our original two equations. Plug K equals 0.17 into one circle means what I've labeled with one circle is equation 1. And we get 70 equals AE to the 2 times 0.17. So that AE to the 0.34 equals 70, just switching sides, multiplying the 2 by the 0.17. So A should equal 70 over E to the 0.34. Now my question is, what number would we cube to get about 2.7? We cube 1.4. 1.4 is pretty close. So, and not fudging that, I could. And that equals 50. Now let's just remember what we got for A in the preceding. We got this portion. Got A is about 54, and it was 70 over 1.36, using a different set of numbers. So we got 54 here, we got 50 here. I think the 54 is a little more accurate. But still, it's a pretty good model. So now we say the model is P of T equals A E to the KT, which equals 50 times E to the 0.34 T. Okay, so that's two good examples. So we have two models that fit our data fairly well. Not perfect, but if you use a calculator to get your numbers, they're going to be more perfect. Of course, are those numbers perfect? You're trying to get the population of fish in a pond. You don't strain the whole pond, count the fish, and throw them back in. You might miss some. You might count wrong. You might kill a few. So the original data, population of 70 after 2 months, population of 190 after 8 months. Okay. 70 after 2 months, 190 after 8 months. Those numbers are a little fuzzy. Not sure it's really 70. You're not really sure it's 190. So even if you have completely accurate results from your calculator, when you start calculating the model, or very accurate results, up to 5 or 6 significant figures, it's kind of meaningless. Okay. Your model is only an approximation. Well, the next thing we want to do with these models is figure out when we're going to get to our goal of 400 fish. we need 400 fish. We got 400 fish, then we know we can catch half of them and sell them. We'll still have a breeding population of 200, and that'll replenish. And we've worked out our business model so that that's the appropriate number. Okay. Let's pose a question. When will the population reach 400? Okay. I'm going to use the second model, the exponential model, because there are things you might want to do with calculus with this model. It was P of t equals 50 e to the 0.34 t. Better for worse, there's no model. We want to know when the population reaches 400. Well, what does that mean? Well, it means P of t is 400, so we substitute 400 for P of t, and we get 400 equals 50 e to the 0.34 t. Yeah, I like the idea that I chose this one because I have a nice number that easily divides into 400. I wasn't planning that, but there it is. Then if we had 54 times 1.17 to the t from the other model, we could write out the similar equation, and we wouldn't need to use any tricks to solve that equation. But here we got to use the exponential to logarithmic form to solve. So we solve this equation. First of all, we'll put the t, which is a variable we're looking for, over on the left side just by switching sides. 0.34 t equals 400. So we get, just switch the two sides. Get 50 e to the 0.34 t equals 400. Then we divide both sides by 50, and we get e to the 3.34 t equals 400 over 50, so that e to the 0.34 t equals 8. Now, using our equivalence between exponential form and logarithmic form, we see that this becomes log base e of 8 equals 0.34 t. Which means, of course, same as natural log of 8 equals 0.34 t. You go to your calculator and evaluate natural log of 8, which is a little more than 2. I'm going to say maybe 2.2. Okay? So we get natural log of 8 is about 2, might be 2.3. I think it's more than 2.1, but believe me. Okay, work it out yourself. You can get a more accurate result with your calculator, but we get 2.2 equals 0.34 t. So that t equals 2.2 over 0.34. 0.34 is pretty close to 0.33, which is 1/3. If we divide by 1/3, it's like multiplying by 3. We get 6.6. I'm just going to say this is 6.5. So after 6.5 years, the population ought to be up to 400. And that just isn't so, because the population is 190 when t equals 8. So what did I do wrong? Probably something. I'm going to pause here, see if I can locate an error. But the process that I've used is completely valid. Okay, looking back, I find that I got a couple of numbers jumbled in my head, just like you could accidentally put the wrong number into your calculator. I didn't do that to provide an example of what you have to do to debug a solution. But obviously, our solution has to be debugged because we get a ridiculous result. We find that the population should be 400 when t equals 6.5. And if we look at our graph or at our data, we find that when t equals 8, which is more than 6.5, the population is only 190, and the population is clearly increasing. So that was obviously a wrong solution. And where it went wrong, turns out, was I was squaring E and then using it to approximate 8. Okay. And I got the wrong numbers in the wrong place, just like you can easily get the numbers in the wrong place when you're punching them into a calculator or some other thing, or asking artificial intelligence, which might well make up the numbers. You can't trust them. Okay, so we get k equals this. Uh, and that wasn't quite right. There's a natural log of 19/7 that I miscalculated. 19/7, as I said at the time, is very close to E. So we get still pretty close to 1.01. Let me stop and think a little more. Okay, now I figured if I found it. I was off camera for good few minutes, maybe even 5 minutes, recalculating some of this stuff using Wolfram Alpha. Found out that my approximations were all really good. Okay, didn't do anything wrong. Any of these numbers, they're very close. When I plug in to the correct model, plug in t equals 8, I get 194 instead of 190. So, it's really, it's doing okay. But you know what I did? We determined the k was 0.17, the model's a e to the kt. What did I write down in front of t here? I wrote 50e to the 0.34 t because I had that 0.34 in my head before. And that led to all kinds of problems. Should have been e to the 0.17 t. Then, if I want to do this check, my 0.34s here need to be changed to 0.17s. Okay, so 0.17 here, 0.17 here. When I plug into P, and what did plug into P equals 50 e to the 0.34t, and got something that was ridiculous. Okay, should have been e to the 0.17t in every step down to where I got my t equals 6.5. So I change all those 0.14s and 0.17s, and now I get t equals 2.2 over 0.17, which I estimated when I divide by 0.34, I estimated 6.5. I'm dividing by 0.17, which is half of 0.34. So I ought to get double 6.5, which is 13. Now, if we plug t equals 13 into the original equation, we're going to get something pretty close to 400. Okay, 0.17 times 13 is 2.21. So the 2.2 comes right. And I think everything is going to work out well. You can plug 13 in and see. Now, again, my point is, number one, got a calculation with a number of steps. There's a good possibility that, like me, you're going to make a mistake at one step. Maybe even two or three. I've been known to do that. My mistake here is very trivial mistake because I wasn't thinking clearly about what I was writing and where the number in front of 2 came from. Look back at my solution for K rather than looking at that 0.34, which was an exponent of E. And to make those kinds of visual clerical mistakes and many other types of mistakes, which is why we check our book. And I checked what I did, found out that it was ridiculous. I mean, what I did was actually pretty good, okay, but came up with a ridiculous solution because of one simple clerical error. It took me a while to find. So, lesson, be as careful as you can when you're doing the steps. It can save you a lot of time in trying to fix errors. And also, save you the danger of not being able to fix your error and not being able to get a result. All right. Well, that's a couple of applications of how we can solve logarithmic equations or exponential equations. Just one quick caveat. Remember that the equation you solve has to be in the form B, the A equals C. Now you might be using different numbers than A, B, and C. Okay. The equivalence only applies to this form, and the equivalence to that is log base B of C equals A. Getting the thing you want to solve for, which is in the exponent, down here where you can evaluate it. And then the log base B of C, if you got numbers for B and C, you just plug them into your calculator. Okay. If you have an equation like 5 times 2 to the 0.8t equals 40. What are you going to do with that equation? That equation is not in this form and it's not in this form. Okay? It has to be in this form. It isn't, but you can easily write an equivalent equation that is in that form just by dividing both sides by 5. Okay? I's in the way. This doesn't fit b to the a equals c form. Sides Divide the left-hand side by 5. Well, that 5 divided by 5 gives you 1. So you can simply write the left-hand side would be 2 to the 0.8t. And the right-hand side divided by 5 is 40 over 5. So you get 2 to the 0.8t equals 8. So log to the base 2 of 8 equals 8t. T then equals log base 2 of 8 divided by 0.8t. And in my classes, I ask people to write out the detail of log base 2 of 8, which is log of 8 divided by log of t of 2, all divided by 0.8, and that can be put into your calculator. You get the log of 4. Log of 4 is about maybe 1.3, divide that by 0.8, and maybe the result is around 1.6 or 1.7. So you can check that out. It's not as careful an estimate as the ones I made over here, so do check it out. Now there's more to solving logarithmic equations, but the bottom line is you got to put it in one of these forms, exponential logarithmic equations, and then convert to the other. Okay, good luck, and let me know if you have questions.